So let's look at the simplest geometries. Let's look at linear geometries. Linear geometries occur when we have a central atom with two bonding groups. There must be two bonding groups. And the way these two bonding groups get as far apart from one another as possible is 180 degrees. And here are two examples. We have beryllium chloride. And remember, even though beryllium's a metal, it has a lot of non-metal character to it, so it has bonds which are very similar to covalent bonds. And here is carbon dioxide. If you draw up the Lewis dot structure for carbon dioxide, there are not enough electrons to give everyone lone pairs, so we've got a share between our carbon and oxygen here and our carbon and oxygen here. And even though we know there are 4 electrons around carbon, thus fulfilling the octet rule, in terms of looking at geometry, we consider there to be 2 electron groups. So these 2 double bonds are as far apart as possible from one another by being 180 degrees. So the bond angle in both cases is 180 degrees, and both molecules are considered linear. Now let's look at the trigonoplanar geometry. When there are 3 electron groups around a central atom, they want to be 120 degrees apart from one another. And here we have a central atom boron with 3 identical atoms fluorine. We know that boron is okay with just 6 electrons, so it's happy with these just 6 electrons. And the bond angle between each boron fluoride bond is 120 degrees, and this is a planar molecule. When there are 4 electron groups around the central atom, they want to be as far apart as possible, and that angle is 109.5 degrees. No matter what 2 angles we look at, they're going to be 109.5 degrees apart from one another. And here we have a simple example, carbon tetrafluoride. Here's our central atom. It's bonded to 4 identical atoms of fluorine, and each bond angle is 109.5 degrees apart from one another. And this shape is known as a tetrahedral shape. Now, we have looked at the simplest case where all the electron groups are bonds and all of the bonds are equivalent, meaning they're the same type of bond and they're bonded to the same atom. However, we're going to have some other cases where the central atom is going to have lone pairs or be bonded to different elements. And so let's look at how that impacts the shape. They're going to be derivatives of the shape, but it is going to have an impact on the overall molecular geometry. So let's remind ourselves, this is the trigonoplanar. If there are 3 electron pairs around a central atom, they're going to be 120 degrees apart. Excuse me, I said electron pairs. I should say electron groups. If there are 3 electron groups around a central atom, they want to be 120 degrees apart. So here's an example of a central atom. This is the molecule of sulfur dioxide. And if we look at our central atom in any of these 3 resonance structures, we see that our central atom has 3 electron groups: a double bond, a lone pair, and a single bond. Single bond, lone pair, double bond, 2 double bonds, and a single bond. In any rate, each resonance structure has 3 electron groups around the sulfur. How do 3 electron groups want to arrange themselves? They want to arrange themselves 120 degrees. However, when we look at the shape of the molecule, we don't put the lone pair there. Sorry about that. All we care about is where the atoms are. But the lone pair is there. There are 2 electrons that want to be as far apart from these electron groups as they can be. So what results is a bent shape. Why is it bent? Because there are 3 electron groups around our central atom. And this lone pair still is electrons and is still repelling these other 2. Now, electron pairs are a little fluffier than electrons being held between 2 atoms. So it's going to push down, repel even more strongly these 2 bonding groups. So our angle it should be 120 degrees, but it's going to be a little bit less because lone pairs are fluffy and can push down and repel more effectively than bonding electrons can. Now let's look at derivatives of the tetrahedral. Here's our tetrahedral shape, and here's our central atom in the most simple case where we have 4 bonding pairs and it's bonded to the same element. Well, what happens if one of these is a lone pair or 2 of them are a lone pair? These lone pairs still want to be 109.5 degrees or so apart from one another. So we have 2 derivatives. If one of the electron groups is a lone pair, then we end up with a pyramidal shape. If 2 of the electron groups are lone pairs, then we have what's called a bent shape. Now, your textbook specifies tetrahedral bent shape, and you may need that to complete your homework correctly or your quizzes through Mastering Chemistry correctly. However, I must tell you that no other textbook or chemist that I know of uses this. They just say bent. Now, there are 2 different types of bent, so your textbook is trying to clarify it, but when you go out into the big, wide chemistry world, don't go saying tetrahedral bent. They'll think you're not very with it. You just say bent. Okay, now for all of these shapes, the bond angle is still going to be approximately 109.5. So let's look at 2 examples. Here is an example of a central atom that has 4 electron groups. They want to be about 109.5 degrees apart from one another, but one of them is a lone pair. So here's our central atom. We still have electrons here repelling these other electron pairs, but the shape, I'm so sorry about that. I hope that didn't bust out your eardrums, because it certainly did mine. But anyway, as I was saying, here we have one lone pair, and what our shape is trigonal pyramid. Trigonal, we have our 3 atoms forming a triangle, and pyramid because the bond angle is still about 109.5 degrees, so it's not in a plane. It's sitting up like a little tripod. And then over here, we have a central atom oxygen with 2 lone pairs. We still have 4 electron groups around our central atom, and they still want to be 109.5 degrees or so apart from one another, as far apart as they can be. However, when we look at the shape of the molecule, we only want to look at where the atoms are. Anytime you have 3 atoms in a molecule, it's either going to be bent or it's going to be linear. If there are lone pairs on the central atom, it's going to be bent. If there are 2 lone pairs on the central atom, then it's going to be what your book calls tetrahedral bent, which means the bond angle is going to be about 109.5. Now, as I said earlier, lone pairs are very fluffy, and so they push down on these bonding electrons. So our bond angles are actually a little bit less than 109.5. And same thing here, we have 2 lone pairs pushing down, repelling our bonding electrons, so our bond angle is going to be less than 109.5.